Okay, so we have our tension test results now. We measured the deformation, which is, sorry about that. There we go, the deformation. We have our load. And you can see all these segments here, 1, 2, 3, 4, 5, 6, and then 7. So we have the elastic region. Anywhere in here is good. That's usually where we want to keep it. We have our elastic limit. We have increased stretching. We have the point where it's going to begin to neck over here. And we have something called work hardening, which we'll get to at the end. We're going to go over each of these points individually, so I won't talk about them too much here. I will just say this, that this is the region you want to be in all honesty. Stay there. It's safer. Okay. So initially, relationship between the increased load and the elongation of material is linear. This is normally where we keep it. However, at some point, the changes in deformation become permanent. However, determining that exact point is terrifying because it takes just so many steps. You keep on going and saying, well, did it go back to the original length? No. Did it go back to the original length? No. Did it go back to the original length? Sorry, yes, yes. Yes, yes. No. Okay, we'll have to start iterating between here and here until finally you hopefully get close to it. But it takes a lot of samples, a lot of experiments, and so we typically just say, okay, we'll say that the elastic limit is here, even though it's actually up here, which is very difficult to find. Now, after leaving the linear region, deformation is much more likely to become permanent. Also, deformation increases much more quickly with increasing load. So it's no longer linear here, but this is still, for many materials, an elastic region. It's just, it's no longer a linear elastic region. All this can still be, recovered. It can still go back to its normal length. But finding exactly where the endpoint is too difficult. So normally we just say, as soon as it's no longer linear, you've reached an inelastic region. Now, this region of advanced deformation is helpful in many ways. So, even though we've gone past the point, like at this point right here, we have definitely reached the area where the material is permanently deforming. It's not weakening yet, but it is permanently deforming. It is stretching, and it's going to stay stretched. But just like when you have a coat hanger and you bend it back and forth, you feel it get harder. And that's because of work hardening. And so when you stretch it, well, yes, it will go back down. It will have that permanent deformation, however much this is. That's going to stay. However, it's now stronger. It actually will take a longer time for it to reach that point of work hardening again. So it's now elastic in a larger region. This is what you can do through processing, and sometimes you just know this is going to happen, so you build things that will be work hardened under their first load to be strong enough from then on. Examples of that might be, let's see, well, perhaps a bridge that will be work hardened by the very first car that drives over it. The car causes it to stretch just slightly, increasing its strength, and then from that point on, every single loading is an elastic loading with a linear relationship. Okay, now eventually a max load is reached for the material. Now, this might not make sense to you because you're like, well, then if the load is decreasing, why is there still deformation? However, load is measured by how much the material resists being stretched and not by how hard the machine pulls. So like technically, yes, your load is increasing beyond this point, but overall, how much the machine actually feels that the material is resisting it is decreasing it. So at this point, it can't take any more, and the material begins to neck. And when it necks, it can't resist the load, and so it's going to begin to go towards fracture. That's no good anymore. We don't want to be in this region. This is a danger zone you never approach. So the load drops. That's because of necking. Less cross-sectional area means that it has less ability to resist being pulled. And then finally, this will approach the point of fracture. Now, for fracture, it will not necessarily neck before it reaches fracture, or at least not neck to the point where you can actually see it. The more elastic material is, the more likely you are to see necking, and even in that case, you do not want to see necking. It's very dangerous to be nearby. And my question for you is now, would these results work for a specimen with a different cross-section? Because this is load, that's just the raw force. This is deformation, that's just the raw change in length. So would these results work for a specimen with a different cross-section? Or, for that example, that is longer. Maybe this is the one I tested, and then this is the one that's going to be used. Will these results be comparable? Is this helpful at all? Well, that's what we're going to find out about next time when we learn about the stress-strain diagram. But you've listened long enough, so go ahead, take a break for now, and then come back and we'll learn about the stress-strain diagram. Thanks for listening.